Welcome to the Weekend Review number 2. We covered quite a bit this week, so I'll try to quickly go over that. So the first thing that we covered is various concepts from linear algebra. So some of these include the notion of independence and dependence, as well as rank. Let me try to write a little more clearly. Rank, eigenvalues, and eigenvectors, as well as how all of these things interact with this function called the determinant. So let me briefly go over these things. So we said that if we have some collection of vectors, this is the concept of dependence here. So our definition is as follows: v1, v2, and v3, and of course this definition naturally extends to any number of vectors, are called dependent if I can find, in other words, if there exists, this is that symbol that we introduced in class, A1, A2, A3, not all 0, some of these can be 0, such that A1, V1 plus A2, V2 plus A3, V3, this linear combination of the three vectors, so this is called a linear combination, is equal to the 0 vector. I'll just put that symbol over there so you know that this is a vector and not just a scalar. So this is what dependent means, and again, of course, it extends to more general number of vectors. So again, v1 to vn are called dependent if there exists coefficients ai, not all 0, such that the sum of ai, vi is equal to the 0 vector. So therefore, independence is the opposite. So v1, v2, v3 are called independent if the only way that I can combine them to make the 0 vector is by multiplying them all by 0. So if a1, v1 plus a2, v2 plus a3, v3 is equal to 0, that implies, in other words, it can only happen if a1 equals 0, a2 equals 0, a3 is equal to 0. And of course, the extension is v1 to vn are independent if the sum of ai, vi is equal to 0 can only happen if each of the ai's is equal to 0. Okay, so that's the concept of dependence and independence. Now, there was this connection, important connection to matrices. And the key thing that's very important to remember with matrices is that what is A times X? Of course, we see this all the time, and all of you know how to do this matrix vector multiplication. But one very good way to think about this is that AX really represents just a linear combination of the columns of X. So let's see that. So let's write A as in terms of its columns. Then you should be able to check that if I look at AX, so this is A, written in terms of its columns, and X, written in terms of all of its coordinates, x1 to xn, that this really equals, as I said, just a linear combination of its columns. In other words, x1, which is a scalar, times the vector v1. Let me just put the symbol over there so it's unambiguous. Plus x2, the scalar, times the vector v2, plus xn, the scalar, times the vector vn, or just sum of xi vi. So this means that if A has columns that are all linearly independent, so linearly independent, then the only solution to the set of equations ax is equal to 0 is x is equal to 0. Again, these are vectors. But if the columns of A are not all linearly independent, in other words, they're dependent, then it means that there exists a vector x, which is not all zeros, such that ax is equal to 0. And let me give you an example of this. So let's suppose a is equal to minus 1, 3, 2, 0, 4, 4, 6, 2, 8. So I claim that the columns of A are dependent. So let's see why this is true. So V1 is minus 1, 0, 6, the first column. V2 is the second column, 3, 4, 2. And V3 is the third column, 2, 4, 8. Then notice that it's possible to combine them in such a way to make 0 without having only 0 coefficients. So 1 times V1 plus 1 times V2 plus minus 1 times V3. Check this for yourselves. This equals the vector 0, 0, 0. And a way to write this in matrix vector notation is that the matrix A times the vector 1, 1, minus 1 is equal to the all zeros vector. So one thing that you can check with MATLAB is that, or by hand, is that the determinant of A is equal to 0. And this leads us to one very important fact that we mentioned, which is that the determinant of A is equal to 0 if and only if the columns of A are dependent. So another way to say this is that, so an equivalent way of writing this fact is the following, that the determinant of A is equal to 0 if and only if there exists some non-zero vector x such that ax is equal to 0. Again, why are these equivalent? Because ax represents a linear combination of the columns of A. And if the columns of A are dependent, then there exists a linear combination that makes them all 0. And conversely, if there's a linear combination that makes them 0, the columns must be dependent. And that's why these two things are equivalent. So we use these ideas to explain the formula, or the fact, let's say, that the eigenvalues of a matrix A are given by the roots of the characteristic polynomial of A. And remember that the characteristic polynomial of a matrix is sometimes denoted by P sub A of lambda. This is a polynomial. And it's the familiar determinant of lambda I minus A. So let's again do a very quick recap of why this is the case. So we know that V is an eigenvector with eigenvalue lambda exactly when AV is equal to lambda V, which is equivalent to saying that A minus lambda times the identity times V is equal to 0. So note, all that I did here is I just brought lambda v over to the left, and I factored out a v from the right. But saying that a minus lambda I v is equal to 0, where of course v is not the 0 vector, this is like saying, this is the same as saying that this matrix A minus lambda I has dependent columns. Right? For there to be a solution, V, to A minus lambda I, V equals 0, that's the same as saying that A minus lambda I has dependent columns. But by the fact above, this means that the determinant of A minus lambda I must equal to 0 if lambda is an eigenvector, an eigenvalue. And that's where that fact comes from. So a few other things that we defined, a few other linear algebra concepts we defined. We said that rank is equal to the number, the rank of a matrix, A, is equal to the number of linearly independent columns of A. And it turns out, we may see this in more detail later, but we haven't given the proof, that this is also equal to the number of linearly independent rows of A. And we also haven't yet seen this, that this is equal to the number of non-zero eigenvalues of A, but counting multiplicity. Okay. Whoops, sorry about that. Okay, so now let's go back to what we've been discussing. We've been discussing stability. And just to remind you, the general flow is that we said that any linear time invariant system, through an appropriate choice of variables, can be written as x dot is equal to ax. So everything, so any combination of mass springs, RLC circuits, and a wealth of other things, as you saw on your previous homework and as you'll see more in the future, can be reduced to this simple form, x dot is equal to ax. And we want to understand stability. When is it stable? So the flow was the following. When we had a scalar equation, x dot equals ax, we understood this completely. When we had a diagonal matrix, x dot equals ax, where A is this diagonal system, A1 to AN, this is basically no different than the case of n decoupled scalar equation. So this is something also that we understood. So the first interesting that we talked about is x dot equals ax when A is not diagonal, but diagonalizable. And we saw numerous examples. So, for example, the matrix 2, 1, 1, 2, we said is diagonalizable. But clearly it's not diagonal. And what is diagonalizable? What's the definition of diagonalizable? A is called diagonalizable if there exists a matrix T that's invertible and T inverse is equal to a diagonal matrix. So recall from last week in review that we saw that this operation, this preserves eigenvalues. So A and D have the same eigenvalues. We showed this, and it's extremely important for us. From a physical standpoint, it's not surprising at all, because how does this transformation take place? If we have x dot is equal to ax, and we change coordinates, z is equal to tx, then what are the dynamics for z? z equals tx dot, which is equal to tax. And if z is equal to tx, that's the same as writing that t inverse z is equal to x, and therefore we get that z dot is equal to t inverse times z. So this means that t inverse is the kind of operation that maps one system to the other, preserving every physical characteristic about it. It's just a change of representation. So that's why, and I went on about this for a while in class, that row and column operations do not have this property. So, in other words, what this means is that if we have system 1, x dot is equal to ax, and system 2, z dot is equal to a hat z, and a hat are related by a hat is equal to t inverse at, or equivalently, a is equal to t a hat t inverse. This means that system 1 and 2 are the same under a change of coordinates. So in other words, they're the same, we've just chosen to look at them or represent them differently. But in contrast, if A and A hat are related by row-column operations, then the systems 1 and 2 could be completely different. So 1 and 2 could be completely different. For example, one of them could be stable and the other could be unstable. Okay, so that's very important to remember. All right, so finally, this raises the question of non-diagonalizable matrices. So what about matrices like the one that I gave in class, which we showed is not diagonalizable? And for this, we had to introduce this concept of Jordan Canonical Form. Okay, so this is a bit of a big piece of machinery that we're not going to actually prove, and it says the following. It says that for any square matrix, I can find some invertible matrix T such that T inverse, again, why do we look at transformations of the form T inverse? Because they preserve all physical properties of the dynamical systems that we're looking at. Is in Jordan canonical form. And J has this special form. It's block diagonal with some number of blocks. And each individual block, let's say the ith block, has this very special form of the same value on the diagonal and ones just on the off diagonal. So for example, the matrix 3, 3, 3, 1, 1 is a 3 by 3 Jordan block. And similarly, the matrix 4, 1, 1, 1, 2 is a matrix in Jordan canonical form. And how many blocks does it have and what are the sizes? Well, it has 3 blocks. It has a 1 by 1 block. So J1 is the 1 by 1 block, which is 4. J2 is a 2 by 2 block, which is 1, 1, 0, 1. Right, so in this case, lambda 1 is equal to 4, lambda 2 is equal to 1. And J3 is equal to a 1 by 1 block, which is 2. So lambda 3 is equal to 2. So this is Jordan canonical form, and we saw some examples in class, and you'll have more practice on the homework. And the key point is the following. If A is a matrix, and TA, T inverse, is equal to a diagonal matrix, then we saw that, so this is the same as writing that A is equal to T inverse dt. Then A to the power k is equal to T inverse d to the power k times t. So this is something that you should be able to check for yourselves by now. And recall the definition of the matrix exponential, e to the at. This is equal to this is in perfect analogy to the scalar case, so I plus at plus a squared t squared over 2 factorial, etc. So e to the at is equal to e to the t inverse dt times t. And if you just plug this into the definition and factor out a t inverse on the left and a t inverse on the right, you'll find that this is equal to t inverse times I plus dt plus d squared t squared over 2 factorial, which is exactly equal to t inverse times e to the dt times t. And the benefit of this is that this middle matrix, e to the dt, we know what it is. It is e to the d1t all the way down to e to the dnt, where I'm saying that d is equal to, I'm using the di's to be the diagonals. So notice that there's nothing special about these calculations here for a diagonal matrix. In fact, it's true for any matrix. So if TA T inverse is in Jordan canonical form, then e to the at is equal to T inverse e to the jt times t. Now the nice thing about e to the dt, it was easy to understand what it means, easy to understand stability, but what about e to the jt? And this is finally what we showed we could also do. So step 1, which you should check yourselves, is that if J is block diagonal with k blocks, so this is block diagonal, then use the definition of matrix exponential to check that e to the jt is equal to the block diagonal matrix e to the j1t, e to the j2t, all the way down to e to the jkt. So this means that all we need to understand is e to the to one of these blocks. So we need to understand what is e to the jit for different sizes of these Jordan blocks. So for a 1 by 1 block, ji is just equal to the 1 by 1 matrix lambda I. So e to the jit is equal to e to the lambda it. So far, so good. For a 2 by 2 block, this is what we derived in class. Ji is equal to lambda I 1, 0, lambda I. And I showed you in class, we computed computed explicitly that e to the jit is equal to e to the lambda it, t e to the lambda it, 0 e to the lambda it. What we didn't compute in class, but you'll do on the homework, is that for a 3 by 3 matrix where ji is equal to lambda I, 1, 0, 0, lambda I, 1, 0, 0, lambda I, e to the jit is equal to e to the lambda it, t e to the lambda it, t squared over 2 factorial e to the lambda it, 0 e to the lambda it, t e to the lambda it, 0, 0, e to the lambda it. So you can see this this pattern, and therefore look at 4 by 4 and so on. So what does this tell us about stability? We want to know the stability of an LTI system. We said we need to know, therefore, the stability of x dot equals ax, which means we need to understand e to the at, but e to the at is equal to t inverse e to the jt times t, and therefore we need to understand just e to the jt. But e to the jt itself is block diagonal, so this means that we really just need to understand e to the jit. So we've simplified this problem considerably. And here's the final, our final answer for stability. So x dot equal to ax if all the eigenvalues lambda I have the real part of lambda I less than 0, then the system is stable. If for some eigenvalue, say lambda I, the real part of lambda I is positive, then the system is unstable, and we don't even need to look at the other eigenvalues. If for all eigenvalues the real part of lambda I is less than or equal to 0, we need to do further checking. We have two cases. Case A is if the real part of lambda I is equal to 0, and the Jordan block Ji that contains this eigenvalue is 1 by 1, then the system is marginally or neutrally stable. However, if the real part of lambda I is equal to 0, and that Jordan block is 2 by 2 or bigger, then the system is unstable. So I'll just leave you with this exercise, which is to understand our discussion in class as to why is a 2 by 2 unstable when the real part of lambda I is equal to 0, but a 1 by 1 would be marginally stable. So why is that? I'll see you on Tuesday, and we'll pick it up from here.